So good morning everyone. Today I will show you an image domain wavefield tomography method based on time lag gathers, and I will also show you an application of this method to a 3D field dataset. So as we know, building an accurate velocity model is important for imaging the subsurface. That's because the quality of the migrated images depends on the accuracy of the velocity model. Differential semblance optimization (DSO) is a wavefield tomography technique designed to reconstruct the velocity model in complex geology. In last year's meeting, I showed you the application of DSO to poor illuminated subsoil area, and the result is promising. However, it's difficult to apply DSO in 3D, and the reason for this difficulty is mainly because of the expensive computational and storage cost of DSO associated with the space lag gathers. Here is a migrated image of the wavefield. We acknowledge Start Oil for providing this dataset used in our research. So for this model, if we want to apply DSO to reconstruct the velocity model, the gather we require to compute for one shot will actually take about 50 gigabytes disk space. And considering we need to migrate hundreds of shots to get the final stacked image and the gathers, the total required disk space can reach like several terabytes. Obviously, this computational and storage cost is too expensive for us to afford. So in my following talk, I will show you an alternative of wavefield tomography method based on time lag gathers, which is more efficient and more practical in 3D velocity model building. So let me start with a simple example to illustrate the idea of using time lag gathers for velocity model building. Here I show you a migrated image of a simple one horizontal interface and constant median model. So the image here is obtained by applying the image condition, which is the cross correlation to the source wavefield US and receiver wavefield UR, and then sum over short J and frequency omega. We know that from the migrated image itself, it's not straightforward to extract the velocity information. For example, if we compare the image for correct velocity and incorrect velocity, for example, high velocity or low velocity, we see that the only thing changes in the image is the position of the reflector. And we are, it's not easy to get the velocity information from the change of the position of the reflector. My colleague Francesco will show you how to extract the velocity information from the image directly using image warping technique. But in my case, I will use extended images as a tool to assess the velocity model information. So in this research, I will use particularly the time lag extended images, which can be obtained by applying the time lag image condition to the same wavefield US and UR. But this time, the cross correlation we apply has the time lag tau preserved. So basically, the time lag tau represents a time shift we apply to the wavefield. And I will show you the gathers, the time lag gathers at the location indicated by the yellow light to illustrate how we can assess the velocity information from the gathers. Here is an example of the gathers for correct and incorrect velocity. You see that in the gathers, you have a dipping event corresponding to the reflection. But more importantly, we see that there's a strong amplitude spot in the event. So this strong amplitude spot actually is the focus of the reflection. So you see that for correct and incorrect velocity, the location of the focus are different. For correct velocity, the focus is at 0 tau. For incorrect velocities, like for low velocity, the focus shifts to positive tau. And for high velocity, the focus shifts to negative tau. So based on this observation, we can actually assess the velocity model information by looking at the location of the focus in the time-lag gathers. And we will use the horizontal distance between the focus and 0 tau as a measure for the accuracy of the velocity model. So we define this distance, this horizontal distance, as delta tau, and use this to measure the velocity error. So for our inverse problem, we can define an objective function based on delta tau, which is simply the L2 norm of delta tau, and we refer to delta tau as focusing error in our method. For those of you who are familiar with velocity model building, you may realize that this objective function is the same as the one used by wave equation travel time inversion. So you may wonder, are these two methods the same because they have the same objective function? Well, in both methods, both delta tau measure travel time error. However, in our method, the delta tau is actually obtained from the common image gathers, which is obtained by stacking all the shots, and we obtain this delta tau in the subsurface. But for wave equation travel time inversion, delta tau is obtained from the common shot gathers, and we obtain delta tau on the known receiver locations. So actually, the delta tau has different physical meaning and have a different way to extract in both methods. So, in my own opinion, I think that although two methods share the same objective function, but they are actually different methods. So, after we define the objective function, we can actually see that why our method is much more efficient than the DSO. So on the top of the slides, I show you both the objective function for DSO and our method. But more important thing to notice here is that in 2D, both methods require to compute a gather. Compute the gathers, which is a 3D cube. However, in 3D, they also required to compute the gathers, which are 5-dimensional hypercube. But in our method, we are only required to compute the gather, which are 4-dimensional hypercube. So this means that our method is at least one order of magnitude. The computational of our method is at least one order of magnitude less than DSO. Of course, when we reduce the computational cost, we also lose the resolution in the final velocity model building, because as shown here, in DSO method, you have both lambda x and lambda y to characterize the reflection. Therefore, you should have higher resolution in azimuth direction. And in our method, we only have tau to characterize the reflection, so we will lose the resolution in the model. So after defining the objective function, we can continue to compute the gradient corresponding to the objective function. So the way we compute the gradient is by applying the adjoint-state method. I believe you are already familiar with this method by listening to the presentation from yesterday. So here I won't cover all the details of the adjoint-state method. Instead, I will only introduce the construction of the adjoint sources because this is the key step of the adjoint-state method. So according to the definition, the adjoint sources is simply the derivative of the objective function with respect to the state variable. So here the state variables are the source wavefield US and the receiver wavefield UR we used before to construct the gathers. So if we use, because J is defined as the square of delta tau, so when we take the derivative, what we obtain is the delta tau multiplied with the derivative of delta tau with respect to the wavefields US and UR. However, here we have a difficulty because the delta tau is not directly dependent of the wavefields. So to get a solution and get the derivative of the delta tau with respect to the US, we will use the same method developed in wave equation travel time inversion, which is the use of the connective function. So I won't go into details here, but simply speaking, the connective function is a function which contains both the delta tau and also the wavefield US and UR. So here we construct the connective function as the derivative of the time lag gathers represented by R here with respect to tau and evaluate at delta tau. So you can see the final result on the right of the equation has both the wavefield US and UR and also the quantity delta tau. So when we have this connective function, we can insert it back into the derivative we saw before, and by using the rule for implicit function derivative, we can obtain the final result for the adjoint sources as shown here. Although this result looks a little complicated, actually we can look at them. We can look at the result at different turns, and then we can get a more clear understanding of the physical meaning of the adjoint sources. So first, we notice that the adjoint sources contain delta tau at two places. So first, delta tau will give a sign and the magnitude to the adjoint sources. That's the role of the first delta tau in front of the equation. And also we have a delta tau which will introduce a time shift applied to the wavefield. So this delta tau will actually introduce a time shift so that the wavefields we simulate later will be synchronized with the background wavefields. And also we notice that in the adjoint sources, we have the background wavefields US and UR, which means the information of the travel time error carried by the delta tau will be interactive with the wavefields. And then this interaction of the information will be propagated again back to the median to construct the gradient. So the rest of the equation are simple. For example, we have a constant scaling factor represented by E, and we also have an I omega term, which corresponding to a derivative in time. So after we get the adjoint sources, we can compute the gradient following the standard receipt of the adjoint-state method. So now I will using a synthetic example first to illustrate the workflow of our method. Here is a 3-layer example, and we see that there's two interfaces. One one is at 0.5 kilometers and the other one is at 1.1 kilometers. And the initial model we use for this example is simply a constant with the velocity of the first layer. So this is the migrated image we obtain corresponding to the initial model. So we see that in this case we correctly image the first layer at 0.5 kilometers. However, the second layer in the image is mispositioned at 1 kilometers. And then we construct the time lag gathers, and here is the gathers corresponding to the initial model. We see that for the first layer, the focus in the time lag gathers is at 0 tau, which is consistent with the velocity model we have. But the focus corresponding to the second layer moved to positive tau because the velocity is lower than the true velocity. And next we will extract the delta tau from the time lag gathers, and this is done by picking the strong amplitude focus from the gathers. So you see the yellow curve here corresponding to the delta tau we pick from the gathers. And after we pick the delta tau, we can compute the gradient using the adjoint-state method. And this is the gradient from one shot and for the gathers in the middle of the model. So in this case, the shot is located at 1.5 kilometers in X and 2.25 kilometers in Y. So we see that the gradient consists of two branches. One is from the source to the image point, and the other branch is from the image point to receivers. Remember that in this case we have receiver all over the surface, so the magnitude of these two branches are different. So in this case, we see that the gradient we compute is from the surface to the image point. However, if you remember, the velocity error we have in this case is only limited to the second layer. This inconsistency is because when we compute the gradient is computed based on the accumulated velocity error from the surface to the image point. So when we obtain the gradient will actually spread the velocity error from the image point all the way up to the surface. However, if we want to obtain the update in this case, then we have to eliminate the gradient in the first layer because there's no velocity error in the first layer. That means when we actually run the inversion using the gradient like this, we need additional iterations to eliminate the incorrect update in the first layer. So if we look at the focusing error delta tau in this case, we see that the focusing error delta tau is 0 in the place of the first layer, but it's not 0 in the place of the second layer. This motivates us to design and mask a mask applied to the gradient such that the gradient is consistent with the velocity error distribution. So we will use delta tau as a prior information to design a mask such that we can limit the update only in the area where velocity model error exists. So the way we construct the mask is simply by computing the accumulated delta tau from the surface to the subsurface. So if the accumulated delta tau is less than a threshold delta 0, then we consider the corresponding area has no velocity error, and we should not update the velocity model in this particular area. Otherwise, we will update the model to correct the velocity error. So using this equation, the mask we compute from the delta tau looks like this. So you see that we have 0 in the first layer, and we have 1 in the second layer, which is perfectly consistent with the distribution of the velocity model error in this case. So after we obtain the mask, we apply to the gradient, and this is the gradient we obtain finally. So you see that now the gradient is only limited to the second layer, so we won't update the velocity in the first layer. So after we obtain this gradient, we can repeat for all other shots and all other gators in the rest of the model. And with this mask gradient, we can actually obtain the final updated model in just one iteration, as shown in these slides. So we see that in this case, we obtain the updated model, which is only in the second layer in just one iteration, and compare this result with a true model. We see that they are perfectly identical in the second layer. So here I use a synthetic example to illustrate the workflow of our method. So now let's go back to the field data example you have seen the beginning of the presentation. So this is the velocity model we use to test our algorithm. In fact, as you will see in the presentation in the afternoon, the wavefield is actually characterized by anisotropy, and this model, which is provided by Standard Oil, is actually the normal velocity extracted from the anisotropy model. However, our algorithm is purely isotropic, so when we apply an isotropic algorithm to the anisotropy model, we don't expect that we can improve the accuracy of the velocity model. So in the rest of the example, I will focus only on the image part. So basically, we just test whether our algorithm can improve the focus of the image. So here is the image corresponding to the initial model. So in this case, we will focus on the reflection event around 2.8 kilometers in depth, because that's the main reflection in this model. So we run the inversion, then we update the model, and this is the image corresponding to the updated model. So compare this image with the image corresponding to the initial model. We see that the main reflector around 2.8 kilometers is stronger and more coherent. Also, notice that the event below, close to 4 kilometers in depth, is also more continuous after the inversion. So to better visualize the difference between the images, we extract the inline section from the model and do a more detailed comparison between the images. So here's the inline section for the initial model, and this is the same section corresponding to the updated model. So by comparing these two images, you will see that the image is improved in terms of the continuity and the coherency. So to assess the improvement in the image, we also construct the angle domain common image gathers. So here are two panels. Here the two panels corresponding to the gathers at two different coast lines. So the top panel is the gather extract from one cross line, and the bottom is another cross line. And each small panel there corresponding to one individual gathers at a particular inline location. So notice that in this case, the event around 2.8 kilometers in depth show residual move out corresponding to the initial model. But if we construct the gathers in the same position using the updated model, we see that now the events become flat after the inversion. So let me compare again. So before and after. So some of you may say, well, you are doing a 3D model building. Why still using the 2D angle gathers? Well, I think, of course, the 2D gathers are more straightforward. But actually, as an advertisement for my talk in the afternoon, I also construct the 3D gathers as more advanced tool for QC the velocity model building. So here is the 3D angle gathers, which is constructed for all reflection angle from -90 to +90, and for all azimuth angle from 0 to 360. So as I will give you more details about the gathers, now let's only focus on the part most relevant to our velocity model building. So if you pay attention to the event around 2.8 kilometers in depth in the left bottom panel, we see that the event shows residual move out for initial model case. But if we construct together for updated model, we see that the move out have been eliminated and the event become flat now. So this is another indication that the image focus is improved, because now we have a more coherent event to stack together final image. So in summarize, we introduce a wavefield tomography method based on time lag gathers, which is efficient and affordable in 3D velocity model building compared to the space lag gathers used by DSO. In the method I show here, we actually design the method to improve the image quality, especially the focusing of the image, and this is demonstrated by the field data example I showed you before. So finally, I will acknowledge Start Oil and all licensed partners for providing the field data example used in this research, and thank you for your attention.